In this video, we're going to start tying together our understanding of limits with this notion of tolerance that we've been talking about. And for some of you, the connection may be clear right away. For others of you, it might take a little while. That's okay. If you're not seeing the connection, just keep watching. Hopefully it will become clear. So I've drawn a picture on the board here of a function f of x where this is true. The limit as x approaches a of f of x is this number L. And I've written here what that means informally. It means as x gets close to a, now what we mean by that is it gets arbitrarily close to a without necessarily equaling a. And that qualifier that x doesn't equal a is important because at a, for this particular picture, there is no f of x. Okay. But as x gets arbitrarily close to a without equaling a, f of x gets close to L. Now, I refer to that as our informal definition. What makes it informal is that I'm using this word close. And that's kind of subjective. What counts as close? Before the pandemic, you might have had somebody who was standing closer than 6 feet away, and you might have been perfectly fine with that. Since the pandemic, if you're practicing social distancing, if somebody gets within 6 feet of you, unless they're a family member or somebody who's in your, sort of safe group, that's too close. Okay. So what counts as close sort of depends on the situation. But close, I can think of as meaning that the distance between things is small. Now, I can formally define distance. Okay. So I need to control, if x is getting close to a, I need to control the distance between x and a. And if f of x is getting close to L, I need to control the distance between f of x, the y value on my function, and L, the number that I'm claiming is the limit. So I'm going to just draw a picture here. If here's my x-axis, and here's the x value a that we're getting close to. Now, if x is close to but not equal to a, there are two possibilities, and I'm going to just draw them in different colors. I could have x over here so that it's to the right of a, or I could have x over here so that it's to the left of a. In either case, I can calculate the distance between x and a. We've been talking about the fact that we calculate distance by just subtracting, but we always subtract right minus left. So here, this distance would be x minus a, and this distance would be a minus x. So at first glance, it looks like I get a different formula depending on which side of a I'm on. However, I can codify it if I take the absolute value of x minus a. That's going to just equal x minus a when that's a positive quantity. Here, if x is to the left of a, x minus a would be a negative number, but taking the absolute value is going to give me the opposite of that. It's going to make it positive. It's going to make it just that distance. So the absolute value of x minus a is the distance between x and a. Similarly, I can do the same thing for my y values. Now I'm going to just draw that as a vertical graph because we're talking y values here. If here's L, f of x might be above it, f of x might be below it. Here, this vertical distance would be f of x minus L. That's the bigger y value minus the smaller. This vertical distance would be L minus f of x. Again, bigger value minus smaller value. But I can get one formula for both scenarios if I simply take the absolute value. So the absolute value of f of x minus L is going to equal the distance between f of x and L. And of course, this is going to be a horizontal distance, and this is going to be a vertical distance. Okay, so if I want to show that f of x gets close to L when x gets close to a, I need to show that I can make this distance small, and that I can make this distance small by making this distance small. So what I'm going to do is I'm going to introduce two variables. I'm going to introduce epsilon, which is going to be, I'll write it out, epsilon is the name of that. That's a Greek letter epsilon. It's going to be a positive variable. Okay. And I can sort of think of it as the tolerance for my y values. Another way of thinking of it is it's my standard of closeness for the y values. So I'd be saying that if the absolute value of f of x minus L, if that vertical distance is less than epsilon, that's what I'm going to mean by saying that these things are close together. That the distance between them is small. It's within this tolerance. But I'm purposely not choosing a specific number for that because I want to be able to show that we can get arbitrarily close. So if I were to say we can get within 0.1 or 0.01 or 0.001, that's not arbitrarily close. That's close by a specific fixed amount. By choosing a variable, if I can show that no matter how strict you set the standard, no matter what tolerance you set for how close you want your y value to get to the value of the limit, that we can force it to get that close, then I've shown that we can make it get arbitrarily close. Okay. And I'm going to introduce another variable. It's going to be a delta. That's also a Greek letter. Now, you've seen a capital delta before. A capital delta looks like a triangle, and we talk about like delta y and delta x for getting the slope, say, of a secant line. Okay, this is a lowercase delta. It's also going to be a positive variable. And I can think of it as being my tolerance for the x values. Or another way of saying that is it's my standard of closeness for the x values. So that we'll say the x values are close if the distance between them is smaller than delta. Okay. But again, it's a variable so that I'm not just looking at one specific case for this number, but I'm trying to basically show that we can get arbitrarily close. Okay. Now, these are the tools I'm going to need to state my limit. So I need to know how to talk about distance between x values and y values, and I need to have these variables that measure my tolerance or my standard of closeness for both the horizontal and the vertical variables that we have. All right, so I'm going to keep that picture up, but I'm going to write out the formal definition of a limit. Okay. So, the limit as x approaches a of f of x equals L means. Okay. Now, notice this is all about the y values. The limit is saying what y value do I expect. So if I'm claiming that the limit is L, that means I'm trying to claim that the y value f of x gets arbitrarily close to L. Okay. Now, the reason that happens is because x is getting close to a. But I'm going to start out by talking about my y values. So I'm going to think of this as sort of a debate. Okay? I claim that this limit is L. And there's a heckler in the audience. And the heckler doesn't believe me. So the heckler says, oh yeah? I bet you can't make your y values get that close. So they challenge me. They give me an epsilon. And they say, I bet you can't get that close. And so I need to now defend my claim. I've claimed that I can force my y values to get arbitrarily close. Somebody claims I can't get this close. I've got to show that I can. The way I'm going to do that is I'm going to say, oh yeah, well, I will see your epsilon and I will raise you 1 delta. Because what I will do is I will find a value of delta so that if I can control how close my x value gets to a, if I just look at the part of the graph where x is close to a by that standard of closeness, I can force my y values to be close using epsilon as my standard of closeness. So basically, this statement will be true if no matter what challenge I get, I can always defend it. So how we phrase that is this. For every epsilon bigger than 0. And I'm really going to think of that as no matter how small epsilon is. Because of course, if I say I want to be this close to something, that's pretty easy to accomplish. If I want to be this close, that's a little bit harder to accomplish. Okay, so smaller values of epsilon are better challenges. But for every positive epsilon, so no matter what the tolerance for my y values are, there exists a delta bigger than 0. I can find a tolerance for my x values such that if 0 is less than the absolute value of x minus a is less than delta, then the absolute value of f of x minus L is less than epsilon. So let's look at these two inequalities, because these two inequalities are basically the way I'm saying x is close to a and y is close to L. Okay. So for this inequality here, this part of it just says the distance between x and a is smaller than delta. So x and a are close if I use delta as my standard of closeness. This part of the inequality is actually very important. This says the distance between x and a is bigger than 0. That's saying that x isn't a. Because remember, when we're looking at limits, we don't care what happens at a. We care what we expect to happen based on the nearby behavior. So this part says x is close to a, and this part says x isn't a. So it's getting close, but not equal to a. And if I do that, if I control my x values, then I can show that what I claimed about my y values is true. That the distance between f of x and L is smaller than epsilon. So that f of x is close to L using epsilon as my standard of closeness. Okay, so when we were looking at tolerance, we essentially had the tolerance for our output was like our epsilon value, and we were trying to find the tolerance for our input, which was a delta value, that would work for that particular number. The definition says you got to be able to do it no matter what value of epsilon you're given. For any positive number, you can force your y values to be within that distance of the limit. You'll notice that for the inequality with the y values, we don't specify that this has to be bigger than 0. We're okay if f of x does equal L. That's totally fine. It doesn't have to, but it can. Okay. But we do want to require that x not be the same as a, because we might have a situation like this where we're taking a limit at a place where the function isn't defined, or sometimes at a place where the function just does something unexpected. Okay. So that's essentially what this means. Now I'm going to just draw a picture here. So again, I make this claim. There's a heckler out there in the audience who says, oh yeah, I don't believe you. I bet you can't get that close. Now I'm going to draw my picture with a fairly big epsilon, so that L plus epsilon would be up here, and L minus epsilon would be down here. Realistically, a good challenge would be a very small value of epsilon. That would just be hard to see. So I'm drawing it big so that we can see what's going on. But the idea is that no matter how small I shrink epsilon, so if I made epsilon smaller, this range of y values that's within that tolerance would be shrinking. It would become much narrower, okay? No matter how small I shrink it, I can force my graph to be within this acceptable range, okay? So if I were looking for my delta, I'm basically going to do what we did in the two previous problems with tolerance. I'm going to look at the graph. I'm going to say, here's where we're at A. If I follow the graph to the left, looks like x1. That's the x value where we first leave that epsilon strip, where my y values become too far away from L. And if I follow the graph to the right, looks like over here there's an x2. That's how far we can go to the right before the graph leaves this acceptable range of y values. So that gives me two potential distances. I'm going to just call them now delta 1 and delta 2. Those are my candidates for my tolerance for the x values. Those are my candidates for the delta. Okay. I want a distance that I can go in either direction, so I choose the smaller one. Because if I go this distance to the right, oh yeah, my y values are still within that acceptable zone. But if I went this distance to the left, now my y values have left that epsilon strip. So this would be a delta that works for that particular epsilon. So the tolerance problems that we were doing are like a lot of the homework problems are going to be in your book, where they're going to basically say, here's a function and a limit, and here's a specific value of epsilon. We're going to give you a specific tolerance for the y values. You go ahead and you find a specific value of delta that works for that one. Sometimes you're drawing in a picture like this. Sometimes you're finding a numeric value. I will just tell you, you've got to justify your answer. Sometimes you might be asked to find the biggest delta that works. Here, this distance right here, that's the biggest possible delta that could work. Because if I go any farther to the left, my y values have left that epsilon strip. Okay. It will often be the case that 1/1,000,000th will work for a delta value. But if on a quiz or exam I say, here's an epsilon, find a delta that works for that epsilon, if you just write 1/1,000,000th, I don't care whether it works or not. I care whether you justified it. So make sure that you understand how to show your work to show that something like that does work. So we're going to do a few more problems like what we've been doing, where we get specific values for epsilon and we practice finding a specific delta. That's just so we can understand how this works, that if somebody challenges us, we meet the challenge. We find a delta so that we say, if I control my x values, then my y values will do what I said they would. So I am right, because my y values will do what I said they would. Okay. And then once we've done that, we'll talk about how we deal with it keeping epsilon as a variable. Because there's no way that I can check every single possible value of epsilon. I can't check them one at a time. I can check individual ones, and I can say, okay, I think this works. I think this would work with other values too, but that's not a proof. So how do we actually prove that it works every single time? We're going to build up to that. We're going to spend just a little bit more time finding a specific value of delta that goes with a specific value of epsilon, and then we'll talk about how to prove it in the more general case.